Okay, let's talk about another type of division process called synthetic division. Let me point out, first of all, that long division always works, so you never actually need synthetic division. Long division always works, but synthetic division, although somewhat limited, it's really nice and easy on a particular special case. And that special case we will see later on when we're talking about zeros of polynomials is in fact very important. Okay? Now, why is synthetic division so limited here? Well, the only type of divisor that you can use standard synthetic division on is a divisor of this type, x minus a, where a is a constant. X here then minus a then is what? A monic first degree or monic linear polynomial. So that's what the divisor has to look like, okay? All right? But if it does look like that, then this is going to be a very quick process, faster than using long division, okay? Now, let's take this first example here. Find x cubed minus 3x plus 7 divided by x minus 2, and we'll use synthetic division here. The first thing I would point out here is our divisor, d of x, is x minus 2. That corresponds to the x minus a here, okay? It might look funny. You might think, why don't we have a plus a there? Well, we'll show you here. It's actually x minus a is the perfect formulation. What would that imply that a is equal to? Well, if x minus a is x minus 2, that would imply that a is actually equal to 2. So one of the most common errors students make is getting the wrong sign on the a there. You need to get that correct, otherwise you've blown the calculation. Okay, now other people have slightly different formulation from what I do, but it does not matter here where you physically put all the numbers here on the page. I like to put my a out here to the left and put a little backwards L containing it, just separating it from all the other coefficients that we're going to be looking at here. Now I draw a horizontal line there, and what I'm going to do is make sure that numerator polynomial, the dividend, is written in descending order and include any missing terms. So here are the coefficients. That's all I put down, the coefficients, not the x's. Okay, the leading coefficient, what's the coefficient on x cubed? It's implicit, it's 1. And then you notice we have what? A missing square term. So if I was to include it, that would be 0x squared. So that coefficient is 0. The next, negative 3, and then 7. So you must write this in descending order before you even begin. And don't forget what? Any missing terms here in your calculation. This is another source of error. Very common for students to forget the missing term. Okay? Now, the first thing you do is not a calculation as such. I want you guys to leave a gap here between this line and this line, like I've drawn here, and just bring this on down. Just bring it on down. 1. Okay? Now I'm going to do this. I'm going to multiply the 1 times my a there, the 2. 1 times 2 is 2. And now I want you to add. This works a little bit differently than long division. Let me explain why we're adding rather than subtracting. That's one reason why we have x minus a here. Okay, I'm not going to show you all the details of the calculation, why it works relative to long division, but this is what happens here. So in synthetic division, you add, you don't subtract, is what I'm saying. 0 plus 2 is 2. Okay, now do it again. 2 times the 2 is 4, and then you want to add these, and you get 1, and then you go 1 times 2 is 2, and now add those. Now you've got a string of numbers here. You've got to interpret these numbers at the end. Okay? I claim this very last number is going to be your remainder polynomial. Now, because I'm dividing by a first degree polynomial, I can suppress any dependence upon x, because if it's a first degree polynomial, the remainder is going to have a smaller degree. That means it's going to be a 0 degree polynomial. That means it's actually going to be a constant, so I really don't need that x there. So this is the remainder. All the other numbers you see here are going to be the coefficients of the quotient, q of x. Okay, so these are coefficients of q of x. Now you could see, if you were imagining long division here, that you would be starting with what? X cubed divided by x, that would be x squared. So the quotient here is actually x squared, 1x squared, plus 2x plus 1. And then just put a comma here. The remainder, suppressing, again, the dependence upon x. The remainder is 9. Okay, so another way of writing our answer, I guess I'll just jump up here since I'm almost out of room, is here's our answer. It's x squared plus 2x plus 1 plus our remainder 9 over x minus 2. Okay, I'll box in my final answer. There it is. Okay, so whenever we're dividing by, so whenever we're using synthetic division and dividing by x minus a there, we're always going to get a remainder, which is just a constant. Okay, so I'll be writing r instead of r of x. Okay, let's try another example. Let's use synthetic division on this one. X to the fourth plus 3x squared minus 5x plus 11. And then I'm dividing that by x plus 1. Okay, you can do this mentally if you want, but it's not a bad thing to do. Right? X minus a equals x minus 1 explicitly. Then you see that a is actually negative 1. Remember, you got to get the signature right on that fellow, otherwise you're wasting your time. Now, the dividend is written in descending order, so we're all good on that. That's just fine. And we want to include any missing terms when we do this. Here, let me focus. We've got 1, x to the fourth, 0, x cubed, 3, x squared, minus 5x, plus 11. And there we go. Bring the 1 down and multiply. 1 times negative 1 is negative 1. Remember to add, not subtract. So we add those, multiply. 1, add, we get 4. Multiply, we get negative 4. Add, we get negative 9. Multiply, we get 9. Add, we get 20. Okay? So you remember the very last number in our list at the bottom is actually the remainder. Okay? The rest of this was the coefficients of q of x. Okay? So here's what my answer would be. I guess I have to smash it in here. It's what? X to the third power, 1x cubed, minus x squared, plus 4x, minus 9, plus our remainder is 20 over x plus 1. And there we go. There's our answer, like that. I usually like this in parentheses there. But there's our answer. Okay? So it's pretty easy to do. All right? Synthetic division, limited, but what it works on, it works really well on. Okay? Now let's talk about an important theorem that you want to remember for the exam, is something called the remainder theorem. Okay? Now, you guys already know this, that if I have a dividend polynomial and I'm dividing it by some d of x here, I get what? A unique quotient and remainder where what? The remainder has degree strictly less than that of the divisor. In this case, that would be a constant because that's first degree, what we were just doing, right? So if I have p of x equals the quotient q of x, x minus a plus the remainder being constant there, then what I claim the remainder theorem says is that the remainder, r, is actually the polynomial, or that you started with, the dividend polynomial evaluated at the value a. Okay? And we'll show you here, the proof is very easy. Let's show you a quick proof here. Now this thing right here that I'm boxing in, that is an identity. Those two sides are equal for all values of x. They're equal for all values of x, okay? So, what happens if I let x equal the particular value a? All right, on both sides of this equality here. I would have p of a is equal to q of a, whatever that is. Now I'm replacing x by a, so that's a minus a plus r. Notice that a minus a is 0. 0 times any number is 0. So I'm going 0 plus r, which is r. Therefore, what I have is p, the polynomial p evaluated at a, is actually equal to my remainder. That's exactly what I have just above for my remainder theorem. Okay? So you want to remember this for the exam. The proof is very easy there. Okay, let's go ahead and use this. Let's see what type of question I'm going to ask you when the time comes. Find the remainder r when p of x equals blah, blah, blah is divided by x minus 3. Now, the first thing you want to do here is recall that the x minus 3 should be what? Your x minus a. That would imply that a, I think you can see, is 3. Now, if I'm just looking for the remainder, we said that the remainder by the remainder theorem is going to be your dividend polynomial. That would be the numerator if it was written like this. Your dividend polynomial evaluated at whatever a is. So I will just write it's the polynomial evaluated at 3 this time. Okay, now let's go ahead and do this. Let's plug 3 in there. Maybe I should use parentheses there. Okay. All right, 3 cubed is 27. 3 squared is 9 times 2 is 18. And I've got plus 21 plus 13. Okay. Let's go ahead and do this. This would be what? 9, right? And 21 makes 30. 30 and 13 is 43. Okay. Now, do you see another way I could have actually done this and got the 43? I could have literally done what? If I'm interested in the remainder when p of x is divided by what? X minus 3, what I could have done is the following. I could have used synthetic division with a equals 3 here and set it up just like I did in these previous situations. The remainder at the end that I would have ended up with would have been what? 43. Okay? Now we have an interpretation of what that remainder is in each case. That's actually what the original numerator or dividend polynomial evaluated or whatever the a is. Okay? This leads to something else. People will often call this synthetic evaluation. Suppose somebody asks you to do the following. Find the polynomial p evaluated at -2 when p of x is given by x to the 4th minus 3x squared plus 7x minus 11. Use synthetic evaluation. So when the time comes and you take your exam, I'll ask you to use this particular method. So I'm going to do this. I'm going to do basically the same thing, but I'm going to use synthetic evaluation, which is just the same basic setup as synthetic division, instead of doing this. Okay? So here's all you have to do. Your a in this case, remember it's p evaluated at a, your a is what? 2. Your a is 2. And you remember your a is always going out there. Okay, so there's your a. Now go ahead and take the coefficients of your polynomial that you're looking at. 0, -3, 7, -11. And all I'm going to do is work this like I would a synthetic division problem. Okay, and then grab the remainder at the end. The remainder at the end should be the polynomial evaluated at -2. Bring down the 1, multiply. What do we do here? We add. Okay, multiply, we get -2 times -2 is 4. Add, we get 1. Multiply, we get -2. Add, we get 5. Multiply, we get -10. And then, is that right? Yeah, now add, we get -21. Okay, -21. So I would claim here's how you would write your answer. P at -2 is -21. That would be your answer, and this would be your work, right? Now, if you don't believe me, another way to double check this would obviously be to what? Go back and just let x be -2 in here and compute this the old-fashioned way. Okay, compute this the old-fashioned way. Let's do that just as a double check. It never hurts. You wouldn't get credit for doing it this way because I did ask you specifically to evaluate the polynomial at -2 by using synthetic evaluation. But I don't know what you want to call this, direct evaluation or something. This will just be for our double check here. So I'm letting x be -2 everywhere in that polynomial. And let's see if we don't get -21 here. Okay? All right, let's just double check. Okay? -2 to the 4th should be +16. -2 squared times 3. Negative 3 is negative 12. We get negative 14 and then negative 11. Okay? Now I'm thinking this way. 16 minus 12 is 4. So I've got 4 minus 14. Okay? 4 minus 14 is negative 10. Subtract that 11 there. Negative 21 indeed. So we get the same answer. Okay, so when the time comes, be prepared to work problems of the kind that I've just mentioned in this video. Okay? All right.